In this video, we're going to look at another important characteristic of electromagnetism, namely the potential, the electric potential. So to introduce some things about the potential, we're first going to look at the situation of a charged plate that we saw in the previous video on the electric field. So we know if we have a charged plate, in this case positively charged, there's an electric field in the vicinity of the plate, which is constant in magnitude if we move further away. So here I draw the electric field lines. They are pointing in this direction. So this means there is an electric field on every position on these lines or in this space that has a vector that looks like this. And so now that we have a field here, we're going to look at a particle. So we have a particle here, a positively charged particle with charge Q, as we used before. And we know that on this particle, the plate will exert a force F pointing in this direction. So, if we would not do anything to this particle, under the influence of this force, it will move away from the particle. So, to position this particle here and keep it here, we actually have to exert a force on the particle as well. And if we would now consider bringing this particle closer to the plate, so we move it from the position A here to a position B here, we have to exert additional force on the particle, larger than the force here, to put it on this position. In other words, we do a work on this particle, and so the particle gains energy. And so just a single particle kept in the field already contains some energy. If we will release the particle, it will start to move. And that energy that was contained in the particle will be converted to kinetic energy, to movement energy. So this energy we call potential energy. It is similar, as we've seen before, to the situation with gravity. If I hold this marker up here, it has potential energy, which will be released if I release the marker and convert it to kinetic energy with an increasing velocity when it moves downward. So it's the same for the situation here. So the particle moving from A to B will gain some energy, and that energy gain we can indicate by a value delta U. So it's the change of energy going from A to B. So I will just indicate here going from A to B. Now we define the potential, the electric potential, delta V, between the points A and B as the ratio of the potential energy difference over the magnitude of the charge that we are considering. So the magnitude of the charge on the particle that we are moving in the field. And so this is what we call the potential difference. And the potential difference is measured in units of volt, abbreviated by a V. And the important thing is that this is always a difference. So we are used to talking about the potential, but actually it is defined as a potential difference, an energy difference per unit of charge between 2 points. Now, how come we speak about the potential? Well, if we look at an isolated charge, so I'll indicate a charge here, and we know again we have the electric field lines moving away from this particle, like this, like this, like this. And if we now bring a particle from very far away in the vicinity of this particle, we can write for the potential difference that we have that this is equal to the potential at the position where we bring the particle to. So say this is at the position R, so the particle comes from very far away here. We bring it to this position here. And so it's the potential at position R minus the position very far away. We call this the potential at infinity. So for this spherical charge, the field will fall away. So when we are extremely far away, it falls away quadratically. This term will be 0. Yeah, and this is what we call the potential of a particle. And for a single particle, a single charge, this potential is given by the constant k that we've seen before times the charge on the particle, so this particle here has a charge q, divided by the distance r at which we consider the potential. Now, how does the potential around such a particle then look like? Well, we've seen that the electric field lines go out, so if we bring a particle here from infinity to a position here, it doesn't matter whether this position is located at distance r in this direction or in this direction or in this direction. It is the same amount of energy, k q over r. So if we consider the same r, the potential is the same. So the potential lines around this particle will form spherical lines around this particle. So here there's another potential line. So this is a specific potential, say V2. This is a potential V3. Here we have a potential V1. And along these lines, the potential is always the same. So we call these lines equipotential lines. And an important thing, as we also see here, is that the equipotential lines are always everywhere perpendicular to the field lines. So the equipotential lines that we have are perpendicular to electric field or electric field lines. Now let's look again at the particle that we are moving from position A to position B here, the particle Q. And so say the distance over which we move the particle is equal to a certain distance delta x. Now the potential difference, so in this case also we can draw the potential lines like we've done here. So the potential lines in this case are perpendicular to the field lines. So they run parallel to the plate. So here are the field lines. Let me indicate the change in position here with a different color. And so this is the vector over which we move the particle from A to B. So now the potential difference is given by the magnitude of the electric field, E times the distance traveled, delta x. And so this is also why in a lot of cases we express an electric field in terms of volts per meter. So you will see that sometimes happening. Now, an important thing here to realize is that this delta V relates to a difference in energy per unit of charge. So that actually brings us to an important alternative way of measuring or quantifying energy, which we use a lot in electron microscopy, which is the electron volt. And the electron volt, I will write that down here. The electron volt is defined as the energy, so the delta U, gained by a charge of magnitude E when it travels over a 1 volt potential difference. So we know that the magnitude of E equals 1.6 times 10 to the minus 19 Coulomb. So that makes 1 electron volt equal to 1.6 times 10 to the minus 19 joule. So this is a very small amount of energy, 10 minus 19 joule. But on the other hand, we see that 1 volt is a very common quantity, so we often calculate in volts. Now in electron microscopy, we may also work with kilovolts, so thousands of volts. And in this case, we often also talk about a kilo electron volt, abbreviated as keV. So this is kilo electron volt. And 1 kilo electron volt, so 1 keV, now equals 1000 10 to the power 3 electron volt. And you will encounter this unit of electron volt and kilo electron volt a lot in the lectures about electron microscopy.